So, if you'll remember back to last module, the story that we've had so far is that we have some correlation coefficient R, and that's just a bivariate correlation between some variable X and Y. We've also considered thinking about this correlation in a regression framework where we actually not only model that relationship, but model the error that's associated in the data generating process in order to start thinking about how to generate uncertainty. And that's what we're going to really be talking about today is we want to not only ask, is there a correlation in the population? We want to also ask, is there a correlation in the population? Or if the population has no correlation, is this sample producing a correlation coefficient that's just going to be the result of some normal sampling variability, right? Like we'll anticipate that there's going to be some samples that we'll get that are just going to be abnormal variations of what we observe. So we want to know, is this one of those instances, or are we actually observing a correlation that exists in the population? So how can we check? Let's think about what we've talked about in previous modules. We're going to conduct a hypothesis test. Now, let's think about what we're actually testing here. We're asking, is there any linear, and I say that in parentheses because we'll talk about how to model nonlinear relationships, but is there any linear relationship between these two variables? And more formally, we're going to write this as our null hypothesis is that rho, remember, because we're making an inference about a population parameter, so out in the wild, is that true underlying correlation between these two variables equal to 0? That's going to be our null hypothesis. So if we find sufficient evidence to reject the null, that would indicate, right, that there likely is a true underlying association out in the population. And what's really exciting is we can even then calculate confidence intervals around our parameter rho, and we'll then talk about how to do that with regard to our regression estimates. Before we go into the steps and how to actually construct confidence intervals around our correlation coefficient, I just want to briefly discuss the assumptions that we have and some kind of important factors to consider. So when we're talking about a Pearson correlation here, we're assuming that both X and Y are approximately normally distributed. And again, that's the sampling distribution, right? So a significant result is also not necessarily going to imply that there is a strong linear relationship. We'll talk about that a little bit more in the next slide. And a strong linear relationship does not necessarily imply statistical reliability. So to drive this point home, I'll ask you to briefly pause and think about, is there an association here? Now, it doesn't really appear that there is a relationship, but can we say anything about rejecting a null hypothesis based on the fact that we don't see an association? No, and that's because we need to construct a hypothesis test in order to claim that there is not sufficient evidence to reject the null hypothesis that a relationship does not exist between the two variables. And think about back to previous modules, what do we need in order to do that? We need to have a p-value. So if we have a p-value that's below our critical threshold, typically 0.05, then we can say that we reject the null hypothesis or not, and we can say that that's statistically reliable. However, even though we have a statistically reliable relationship, the correlation itself is very minimal. It's only 0.04. So this drives home the point that there can be a weak association that is statistically reliable or significant, and we can also have a very strong relationship that is not statistically reliable. As a general rule, though, as the number of observations increases, the correlation can be statistically different from zero, even though the linear association is weak. And again, that's just kind of a function of what's going to be in our denominator, right? We will always have more precise estimates when we have larger numbers of observations in our sample. That doesn't necessarily mean, though, that the relationship will be stronger. Just our precision around the estimate will be. So in order to make an inference about our correlation coefficient, we need to have a couple of things. Remember, going back to our hypothesis testing, we need to have two quantitative variables, an x and a y. We'll set up our hypothesis test such that our null is that there is no relationship between the two variables. Our critical threshold is going to be 0.05. So in essence, the confidence intervals that will be surrounding our test statistic will be 95% confidence intervals. And then we'll take an estimate of our sample correlation. That's going to be small rho r. We'll generate that test statistic, right? And we'll talk about what that entails. We'll get a p-value then, and then we can make some sort of inference about our null hypothesis. So let's construct this by hand. Remembering that our calculation for small r is just the covariance between x and y, and in the denominator, the standard deviation of x multiplied by the standard deviation of y. So we can rewrite that like such. I'm not going to get too far into it. This is essentially the same thing that we talked about last week. So we're going to do this by hand in R. I've first set up our matrix such that x is one variable, the first column, and the second one will be y. We'll then take the covariance between x and y divided by the standard deviation of x, that first column, times the standard deviation of y, the second column, and we get r, again, lowercase r, as 0.87. Now that we have our estimate for the correlation coefficient, we can go ahead and construct our test statistic, which again is going to be just our correlation coefficient, r, multiplied by the square root of n minus 2 over square root of 1 minus r squared. We can do this in r really simply. The only thing that we don't have is just the number of observations. So that's what n is equal to here. And then if we go down to the test statistic here, I've just calculated out exactly what that was, like we talked about, and we get a t statistic of 3.54. With our test statistic in hand, now we can calculate our p-value, remembering one, that we're referencing the t distribution, so that's why we're doing pt. Two, remember the degrees of freedom here is n minus 2. And the third thing is that we're multiplying this by 2 because we're doing a two-tailed hypothesis test, right? We want to know whether or not there is any relationship. So it could be positive, it could be negative. And there's no real surprise, right, that we get a low p-value that's below our critical threshold because our test statistic does seem to be extreme enough to suggest that under the null hypothesis that there is no association, this sample is highly unlikely, right? We are finding sufficient evidence to reject the null that there is no association because this is such an extreme test statistic that's generated by this sample. As always, there's a much simpler way to do this in R. There is a function that already calculates a correlation coefficient, and you can tell it what method. In this case, remember, we're using a Pearson correlation coefficient, and we get the exact same thing that we calculated before, suggesting that there is a relationship, right, of 0.87. And we can test whether or not that is a statistically significant difference, right? We've calculated that there's a strong association, but we want to check whether or not this is actually a likely, I guess, correlation coefficient to calculate if there was no association, right? So we can run a cohort test between X and Y, and we get the exact same answer that we did before, right? Our t statistic is 3.54, which results in a p-value that is below 0.05, lending significant evidence to suggest that we can reject the null hypothesis, that there is no relationship between the two variables.